All right. Today we are moving along. We're still sticking with trigonometry, but we are learning some new rules. You can't really, they're not really identities, but they might help us verify trig functions. We could use these for solving, but a lot of times we use these for evaluating trig functions that maybe normally we wouldn't be able to just using, without using a calculator. If you have a calculator, then it's a lot easier to evaluate your trig functions. But these are known as sum and difference functions or formulas. So we have 6 of them, two for each basic trig function, 1 addition and 1 subtraction. So here I use u and v, but they, it could be x and y, or alpha and beta, or theta and psi, whatever it may be. So for sine, when we add, and I will say this too, it might be a little confusing on how we use it here, but once we start jumping into examples, hopefully it becomes a little more clear. But if I am adding 2 angles and I take the sine of that angle, it is the same thing as if I do the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. So notice how they swap there. All right, and this is an addition, and this is an addition. So we have sine of the first, cosine of the second, and then in the second part, you swap it, cosine of the first and sine of the second. When we subtract, it's similar setup, but we just change addition to subtraction. All right, so for your sine function, you can have this alternating sine, cosine, cosine, sine, sine, cosine, cosine, sine, and then you add or subtract accordingly, okay, respectively. For cosine, it's slightly different. Okay, with cosine, we keep cosines and sines together, and the addition and subtraction is opposite. So the cosine of 2 values, u plus v, becomes cosine u cosine v minus sine u sine v. And for subtraction, we flip it. Cosine cosine plus sine sine. Now, with tangent, we use a combination of all of this, and we have very particular setups for tangent. I gotta sneeze. It's probably not gonna come. Give me a second. No, it's right there. No, not gonna sneeze. So the tangent of the sum of 2 different terms, we have tangent u plus tangent v, so the numerator goes along. And then in the denominator, we have 1 minus the product of tangent u times tangent v. So we got both addition and multiplication there. For subtraction, we swap our signs. So it's going to be tangent u minus tangent v over 1 plus tangent u times tangent v. All right, so I'll give you another minute if you need to finish copying these down. All right, along with the other identities that I put up, when we're finished going over these, I will put a reference on our Google Classroom for this as well. Now, unfortunately, these are not the final rules that we are going to learn with sine and cosine. There are a few more. Almost there, almost done. I know I keep saying that, but oh, I forgot about that. Okay, but yeah, almost done. All right, so I'll give you one more moment. I'm going to write down some examples down here to highlight when we use these. Okay, so let's start off. Now, with these, we can use these rules with either radians or degrees. I will admit it is a little easier when we're dealing with degrees. But again, you can, it doesn't matter what we're in. So we're going to do something also a little different. I've mentioned this in the past, but we are going to find the exact value, which means if we have a radical, if we have a square root, we're going to leave it like it, and we're just going to simplify the expression. We're not going to calculate and get a decimal answer. Okay, so I want to find the exact value of the sine of pi over 12. Well, a good way to find the exact value of trig functions is by using our favorite, the unit circle. But we encounter a slight issue here. On our unit circle, there is nowhere that has a denominator of 12. Right? None of these I can make to pi over 12, 1 over 12 times pi. So what we do is we split up pi over 12. So we need to think, and this is where it's a little hard in radians because now we have to think in fractions. Is there a combination of either adding 2 degrees or subtracting 2 degrees that would get me pi over 12, or 1/12 times pi? Well, addition is probably not going to work, because in order to get 1/12, I'd have to add 2 smaller fractions together. So maybe subtraction will work. So I can say that pi over 12 is the same as pi over 3 minus pi over 4. Right? If we find the common denominator, that would become 4 pi over 12 minus 3 pi over 12, which gives me that pi over 12. Right? So it's a little hard to recognize that right away. It might take you some, trial and error to find a combination here. When we are in degrees, and I'll show you an example with that, you'll see why it's a little easier. I picked pi over 3 and pi over 4 because those are, in fact, on the unit circle. So we can find exact values if we'd like. But first, I'm going to rewrite this. I'm going to say that this is equal to the sine of pi over 3 minus pi over 4. That's a pi. So I can rewrite this expression as this, and then this I can use my sum and difference formula. In this case, the difference formula. All right, so this is going to become the sine of the first times the cosine of the second minus the cosine of the first times the sine of, I'm running out of room, the second there. All right, hopefully that's not too sloppy and you can see what I'm saying there. Okay, so again, sine of pi over 3, the first term, times cosine of the second. And then our rule tells us we keep the minus, and then we swap the cosine and the sine. All right, be careful here, right? Although we swap, make sure that the angles stay, right? This is your first angle, second angle, first angle, second angle. I don't want to rewrite it cosine of pi over 4 times the sine of pi over 3, because then I'd just get 0 and they would eliminate each other. So be careful there. Just a word of warning. So now I can find the values for all of these. Right? So let's bring up that unit circle. I'll minimize it. Minimize it. Nope, that's closing it out. That's not what I wanted to do. And really all I need is that first quadrant there. I'm only looking at these 2 angles. right? So the sine of pi over 3, sine is the y value. So the y value of pi over 3 is root 3 over 2. And I'm just going to put it in parentheses because we're going to be multiplying. The cosine of pi over 4, cosine is the x value, but it doesn't matter for pi over 4. Oh, I thought I could point to it, but I guess I can't. They're both root 2 over 2. It's minus. Now we have the cosine of pi over 3, so that is going to be 1/2. And the sine of pi over 4, again, is root 2 over 2. So after this step, after you've found your angles, you're just going to simplify. Right, so I'm going to work with each one of these separately. PEMDAS, right? Multiplication first. Root 3 times root 2 gives me root 6. 2 times 2 gives me 4. Minus 1 times root 2, which is root 2. 2 times 2 is 4. They already have a common denominator. And this is my final exact solution. And we're going to leave it just like that. Okay, again, I don't want a decimal. That's as simplified as we're going to get. And it's as precise as we're going to get. All right, but just to double check, I'm going to do two things. I'm going to calculate sine of pi over 12. So I get 0.25882, or, we have the whole thing there. And now I'm going to calculate this, just to double check. So I'm going to have the square root of 6 minus the square root of 2. That's all going to be divided by 4. And look at that. We get the same exact decimal representation. All right. The reason we don't use either of these, though, is because this, I'm subtracting two irrational numbers. So this is going to be irrational. It's going to go on forever, non-repeating. Right? So if I round this, and maybe I say 0.259, and then if I need to use this in the future for something else, it might set me off. Okay, so we use this equation for an exact solution. Right? Any questions about that? All right, let's take a look at an example with degrees. What do I want to do? Let's do a tangent one. I want to find the exact value for the tangent of 75 degrees. Now, it's a little simpler when we have degrees because we know what degrees we like working with. If I could get a 30, a 45, and a 60, that's perfect. That's great. I may have to expand and use some larger numbers. Okay, you can use the larger numbers, especially if you're subtracting, right? 150 minus 30 gives me 120, even though I already have 120. Or maybe 135 minus 30 gives me 105, right? So 105 is not up here. That's a good way to do that. Or you could do 60 plus 45. So usually with these, just like with most of the trig, there's more than one way to do it. All right. So there's no wrong way as long as it makes sense. So with 75, Well, what numbers can I use for 75? I can use 30 and 45, right? If I add those together. So I'm going to rewrite this and say that this is the same thing as the tangent of 30 plus 45. All right, so you're going to go back and you're going to reference your rules. Tangent always confuses me, so I need my own reference. So I'm going to have the tangent of the first one plus the tangent of the second one all over 1 minus tangent of the first one times tangent of the second one. All right, so the other thing here that I know we haven't really gone over this, and it's another reason I chose this, is using the unit circle to evaluate for tangent is something that I think we practiced a little bit, but I haven't gone over it too in depth. So another thing to remember is that tangent is sine over cosine, and if we're talking about coordinates, it would be the y coordinate over the x coordinate. So what I'm going to do first is I'm going to evaluate the tangent of 30 and tangent of 45, so I don't have a whole lot of fractions. If I just tried to set it up like this, I'd have a fraction plus a fraction over 1 minus 2 multiplying fractions. So let me try to simplify things first. So the tangent of 30 degrees. Oh, another thing that I will say, when we are adding, it does not matter what order I have it. I could have the 45 here and the 30 here. If we are subtracting, obviously it matters because 30 minus 45 gives me something different than 45 minus 30, right? So when it's addition, the way it's set up here, it doesn't really matter how you plug it in. But if it's subtraction, then you gotta be careful. So the tangent of 30. So looking at our 30 degrees over here at our unit circle, the y is 1/2, the x is √3 over 2. So I'm going to have 1/2 over √3 over 2. I keep, change, flip. Okay, I skipped a step in simplifying, but the tangent of 30 is √3 over 3. Okay, or 1 over √3, but we make it look nicer. The tangent of 45, well, they're both √2 over 2. So that works out nicely. And the tangent of 45 is 1. Okay, and I would even recommend doing this setup for the others until you get comfortable. Okay, so for the last one, right, I could have did separately. What is the sine of pi over 3? What is the cosine of pi over 4? Write those to the side and then just plug them in here. Okay, but that's up to you. That's that you can use. Again, if you're not comfortable just plugging in right away. So now I'm going to plug all this in to here. So the tangent of 30, √3 over 3 plus 1 over 1 minus √3 over 3 times 1. All right, so we get some interesting things here. √3 over 3 plus 1 over 1 minus √3 over 3. So we have a slight issue here. It is an exact form, but it's not nice for a few reasons. I have a radical down here in the denominator, and I have fractions with fractions. All right, we usually don't like that. So let me try to simplify this as much as possible. So one thing I can do here, I can multiply everything by 3, top and bottom. in order to get rid of the double fraction. So this would give me root 3 plus 3 over 3 minus root 3. Now, with this part, okay, this is something that we haven't done in a while. I think you should remember the name, though. In order to get rid of this, I'm going to multiply by the conjugate. So in the denominator, I get 3 times 3, which is 9. 3 times root 3 times negative root 3 times 3 cancel out. And then this would get me negative root 9, which I'll simplify in a second. Now in the denominator and the numerator, I have 3 root 3 and another 3 root 3, so that's going to be 6 root 3. I have 3 times 3, which is 9. And then again, I have a 3 root 3, so I have plus 9 there. So this and this both give me 3. Dealing with a lot of 3's here. So this is going to stay 6 root 3. I combine these to be 12. 9 minus 3 is 6. And now, because each part of these are divisible by 6, I can divide everything by 6. And our final answer is root 3 plus 2. All right, so there's a lot of simplification there, some stuff we haven't touched upon in a while. But just be prepared for that. Any questions? That was a little lengthy one. All right, and real quick again, I'm just going to double check. So first I'm going to take the tangent. Oh, let me make sure I'm in degree mode. I'm going to take the tangent of 75 degrees. So I get about 3.732. Let me add root 3 plus 2. And that gets me the same exact thing, 3.732. All right. Any questions?
Can you please use the calculator? Thank you.
I'm not gonna lie, I thought this was gonna be really simple. I was like, yay, we're done. And then you said, oh, we have some simplification. I said, no.
Oh, what? Yeah, what, going from here to here?
Yeah, my brain just said, I'll leave.
Okay, we could spend some time practicing with this. I mean, in all honesty, that's really all there is to it. There's some fancier stuff that we can do, but I'm going to hold off on that for now, because I don't think you really need it unless we're going into yeah, we'll practice with this stuff a little bit longer. It'll take some time. I do want you to try one problem tonight. It's not going to be like this with tangent. It'll be a cosine or sine problem. And then we'll go over that tomorrow. All right, guys. Have a good day. I'll see you tomorrow. If you're still copying down, you can stick around. I won't go anywhere.
Bye, Mr. Murray.
Bye, you too, Mr. Murray.
Bye-bye. Thank you.